All right, class, we're resuming Networking 102 lecture, and we're going to cover the layers above the network layer, so layer 4, the transport layer, and layer 7, the OSI model, the application layer, as well as layer 5, the session layer, for what it provides us with SSL and SSH. And we're going to revisit IPsec back at layer 3. We're also going to cover DNS and DNS attacks, attacks against TCP that provide denial of service. Then also we're going to cover host discovery, port scanning, service discovery, operating system fingerprinting, and then incorporating network programming into shellcode design. We've covered layers 1 through 3, and we're going to cover 4, 5, and 7. 6 is kind of not what we're going to be concerned with. So we're going to cover layer 4, and in this diagram is TCP, but there's also UDP. And the layers below it, such as network layer, are concerned with communicating the physical media up to the point of moving it between computers across the internet. And routing effectively provides this, and provides it at a best effort approach. There is no retransmission of lost data at this layer. It only concerns about getting the packet to its destination and communicating possible errors if the firewalls between the 2 points allow the communication of ICMP messages back to the source of the traffic. But for the transport layer, it's more concerned with not communicating host to host, but service to service. So it's concerned with not IP address to IP address, MAC address to MAC address, but instead source port to destination port. And so transport flows are defined by port-to-port communication. And applications are usually associated with port. There's a list of well-known ports you can find on Wikipedia and other sites as well for services that were established very early on and designated a port that was basically standardized. So you'll probably be familiar with port 80. That's the standard port for unencrypted HTTP web traffic. And so source ports do not need to be chosen according to a standard. They can be dynamically selected. However, ports under 1024 are considered well-known ports, and dynamic selection usually does not stomp on these already. So having a list of well-known ports allows you to go about discovering services that might be running on a host. And the most common way of discovering services is port scanning, simply trying to connect to a port and see if there is a service responding on that port. However, a service need not respond to all requests that are sent, all connection requests that are sent to it. And there is a connection scheme called port knocking that requires connecting to a host over a various number of ports in a very specific way in order to trigger a response from a service. It's basically a secret knock. You have to get it just right. So outside of discovering port knocking services, discovering standard services, which is 99% of all the services running on the internet, is simply handled by port scanning. And there are various different tools for this, and we're going to cover them in a little bit. And there may be various types of applications for each service. For instance, there's various different web servers, there's various different HTTP servers, there's various different operating systems and the basic services that they may provide as well, such as Samba shares and perhaps SNMP handling, etc. And so there are ways to fingerprint exactly what services, what application, and perhaps the version of that application are providing the service when you scan it. And so this is called application fingerprinting, as opposed to just detecting whether or not it's up, which is more so just port scanning. So, but we're getting a little ahead of ourselves. We need to cover TCP and UDP a little bit first in order to cover that material. So TCP stands for Transmission Control Protocol and is designed to guarantee reliable and ordered streams of traffic. However, in order to do this, there's error checking and there's sequence numbers and there are retransmission algorithms, and the control provided by TCP imposes overhead, um, and this requires essentially tracking the state on both the there's overhead not just in the added information to each packet, but also in the memory as well as clock cycles occupied by both the source and the destination of TCP traffic. So this is important to consider when comparing it to UDP. So TCP requires tracking the state of each TCP session on both the source and the destination on both ends of any TCP session. And despite what most courses teach you about video streaming and streaming media on the internet, you will find that most most common streaming services actually opt for TCP over UDP, interestingly enough. So TCP header contains a source port, a destination port, a sequence number, an acknowledgement number, a window size to specify how much room I have in my buffer for your next messages, and then a checksum, which if you're fuzzing anything over TCP, any packet-based fuzzing, you're going to recalculate that checksum to pass that basic constraint at the layer 4 in order to make it even to layer 7, your target application. Usually you're just going to be sending whatever you're fuzzing over some library function. Say if you're doing it with Python, you're going to just have the raw data and you send it, as opposed to replaying the entire packet. Because if you replay the entire packet, the state of the TCP session may not be in the exact state that you need it for the application to handle it accordingly, let alone the state machine of TCP to pass along up to the application without saying, hey, this doesn't make any sense. Why are you sending me this now? We haven't even established a connection. You have to at least buy me wine first, kind of deal. So TCP starts off with a three-way handshake where the first request from A to B is a SYN. And it starts off with a sequence number, and then machine B, if it accepts the TCP SYN request, it will reply with a SYN ACK, and it will acknowledge the sequence number provided by machine A by incrementing it once, and then it will also provide its own sequence number, and machine B will ACK by incrementing machine B's sequence number by 1, and that will be effectively the three-way handshake. Now, this obviously has to keep track of what my sequence number was for machine A. It was 100. Now the reply says it's 102. Similarly, for machine B, it has to keep track of the sequence number 511 and then 512. And a way to attack TCP services is effectively to flood SYN messages and not care about the three-way handshake at all, just continually starting more and more three-way handshakes. And all implementations of TCP won't hang there forever, waiting for this SYN ACK. There will be a timeout on machine B's side. However, between the reception of the first SYN to the timeout, it is occupying memory and perhaps through the spawning of a child process to handle the connection. But at least on the operating system's TCP IP stack, it's going to be occupying memory, at least in the network card buffer, if not in RAM if it gets pushed up to there. So if you have millions of machines connecting to a single server, each one just setting a SYN is getting handled, that's potentially a very large amount of memory that's being occupied on a large amount of clock cycles that are being wasted by just a SYN flood. So that's effectively what a SYN flood is. You send it as much SYN packets as you can to saturate its ability to handle legitimate requests and thus deny its ability to handle legitimate requests, if not just degrade it or disrupt. So the one way to combat it against this is that firewalls protecting any server can be set to do very basic stateful packet inspection to throttle down the number of half-open connections. However, it's limited in its ability to defend against this very primitive attack. So back to the sequence numbers and how those are chosen. There's usually very specific algorithm that is used to choose the sequence number, and it must be chosen carefully, otherwise an attacker can guess it. And since IP allows you to spoof both destination and source IPs, and the MAC address can be spoofed accordingly as well, anyone can inject TCP traffic if they can guess the sequence number correctly, and this is effectively what is known as session hijacking. So SYN cookies are chosen based off a number of bits that are some crypto operation on the string containing the host IP, the host port, the destination IP, the destination port, as well as a timestamp. And that's all encrypted and put here. And then there's it is appended by maximum TCP size segment, the segment size rather, and then also a timestamp that's modded by some number. Usually it's going to be 32. And this is used as the initial SYN cookie construct, and for both from the SYN and also replying to it, the SYN ACK. And so if you can guess this or you can observe it, you can take over a session after the three-way handshake is performed, and perhaps also after the initial authentication up at layer 7 is performed as well, and hijack an entire session at layer 4 after layer 7 authentication, to put it in those terms. So in order to do this, you have to be able to, if you're on the local network, you're able to see all the traffic. If it's a wireless network or if it's a hub. Switches, not so much. You're going to have to do some network trickery in order to redirect all the traffic to you as well. Perhaps you're hacking the switch or the router to forward traffic to you as well. And if you can see all the traffic, you can simply inject anything you want at a very near future sequence number. Originally, sequence numbers were incremented predictably, usually by 1. And fairly early on, probably back in the 2000s, most operating systems, TCP IP stack, started incrementing the TCP sequence number by a random value in order to prevent such session hijacking attacks. However, that random value, it depends on how random it is, and it may still be attackable for some operating systems' default TCP IP stack. Now, for a blind approach, if you cannot see the traffic, you're going to have to guess the sequence number, and that's going to usually require a lot of brute forcing, which may raise IDS flags as well. So Effectively, what you're trying to do is after a TCP handshake has occurred and maybe any higher level authentication at upper layer has occurred, hijack the session by guessing the sequence number and then injecting your own traffic and trying to hand off the connection. If you can control the routing between client and server to reroute to you, to then thus effectively hijack the session. If you cannot, you can perhaps inject one or two TCP packets before the application falls apart. Perhaps a later part of the session requires you knowing the cookie that was stored on the client that you may not be able to decrypt or guess or brute force, and thus you would fail any further authentication requests, such as interpage navigation usually requires sending a cookie for each post and GET request at the HTTP layer, and we're going to cover that in later lecture. So in order to even navigate to a web page, there is a service called domain name systems, because human beings cannot remember IP addresses. That's why we have URLs. So DNS is designed to be a hierarchical service to resolve domain names to IP addresses, and the namespace is divided into non-overlapping zones. So for domain.cs.fsu.edu, there are going to be various DNS servers. The uppermost one is going to be the .edu, which is the last three characters here, which is usually the URL suffix, and whatever happens after this is usually in the form of a slash and then some specific resource that is requesting from the given server. So then past the uppermost DNS server for the edu domain will be a domain server for the fsu.edu domain for all the departments of the FSU, all departments and colleges of FSU rather. And then there will be another name server for the subdomain cs.fsu.edu. You can have a number of DNS servers per zone, usually for providing reliable availability. And DNS does use TCP to facilitate zone transfers. However, DNS responds to all domain name requests via UDP. That's an important thing to note on this bullet point. So, like many parts of the internet when it was originally designed, there was no security considered, and there are a number of ways to attack it. DNS as a service, you can do cache poisoning, you can do full zone transfers to map out a network, you can do denial of service style attacks, amplifying DNS requests to point to a victim or a target rather. And effectively, when a user tries to request, say, www.domain.com, its web browser or operating system is going to contact the closest name server it has, which is usually the DNS server provided to you by your internet service provider. And your computer will ask that name server to look up the address of domain.com. If it has it in its DNS cache, it will reply that domain.com is at x.y.z. blah 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 IP address. And if it doesn't, it will contact the authoritative. It will contact the root name server to find out who is the authoritative server for domain.com or the destination zone domain rather, and the name server will reply with the address of the DNS server that is the authoritative server for that domain. And so the ISP will reply to you, say, hey, go ask this guy. And this guy is the authoritative name server for your destination. And so You go do that, and it replies that 1.2.3.4 is the IP address for your given URL. So DNS communication, as I said earlier, uses UDP to do all of this. And perhaps the only security that it has in this is that requests and responses have a request number, and that's a 16-bit, rather a short number, um, to keep track of that transaction. And servers can be configured as I said, authoritative name server, which is the one that is officially responsible for answering requests for a domain, or a recursive one, which passes on requests to other authoritative servers. So the the root name server here replies with who is the authoritative name server for the given domain if it doesn't already store it itself, if it's not already an authoritative server for that given domain. So servers can also be configured as both, and that's where it becomes complicated, and they can also be misconfigured. So very old implementations of DNS would just accept any information it gets in a reply, and anyone could pose as a false authoritative name server and say, hey, google.com is actually here. Send all the traffic going to google.com here. Or send all the users looking for google.com to this IP address, should be what I said. Now, in order to do cache poisoning on servers that require a correct transaction ID, you simply just have to brute force 16 bits and trigger a request at the same time while posing as an authoritative name server as well. So effectively, what you do is you send a large number of queries to the victim name server, all for the same domain name, and the attacker also sends spoofing from a different IP address, which is going to be the IP address for the root name server or the authoritative name server, saying, hey, this is the IP address for this request. So it's spoofing both ends of the communication here between, going back to this slide, between the end user as well as the root name server or any other intermediate server between it and the eventual authoritative name server. And so it's posing as end user and also as the authoritative server in order to convince the intermediate name server that, hey, you should cache this malicious IP address as the destination for this domain name. So whenever a victim comes along trying to access that domain name, it will be provided your malicious IP address instead. So given that DNS is inherently insecure, DNSSEC has come about, but it's been under development for over a decade and it's not really been deployed yet. It's only providing authentication and no confidentiality to whatever domains you're requesting. Obviously, many users would be uncomfortable with someone keeping track of all the domains that they visited on the internet, especially if you're aware of how many domains you access by a single visit of any site with tons of advertising. Perhaps half of your traffic touches nefarious domains without you knowing it. Nefarious, if not downright suspicious, I should rather say. So, DNSSEC doesn't provide any confidentiality, and it's related to RFC 3833, and it uses a hierarchy of established secret keys to verify the identities of DNS servers between each other so that they don't fall victim to cache poisoning without a compromised key, which raises the bar for attackers to obtain a key either via hacking a name server or by breaking the crypto algorithm that's used to establish the keys, which is much more difficult. But nonetheless, all efforts to secure the internet are really reactionary because the internet was not designed with security in mind. It's all just designed to efficiently transport data from point A to point B. So going up towards the application layer, SSH came along after, I guess, people woke up and realized that its alternative or predecessor, RSH, which is remote shell for Linux and Unix systems, has no security whatsoever, and SSH came about to provide integrity and confidentiality to a remote shell session. So it can be piggybacked to provide SSH tunnels and other things. And effectively, it is built on top of SSL and TSL, or this should be TLS, it's a typo. These are not my slides, I should add. So you should all be familiar with it. If you're a CS student or have done any programming at FSU, you have to SSH in to the server. Your username is sent in plain text, and your password should be sent over encrypted encrypted session key that you've established. And prior to SSH, I said RSH, RLogin, Telnet, etc. Everything was sent in plain text, which was obviously not a good idea. So logging in with everything in plain text is a problem for applications above the complexity or the simplicity of SSH. So web traffic, obviously you shouldn't log into a website if it's not HTTPS because your credentials will be going over the wire or over the air in plain text or clear text. And anyone can view them, save them, and then log into your account, whatever it may be. So SSL provides security for both web traffic as well as SSH and other sessions and other applications and services that rely on it. It was designed back early on by the Netscape group, and I talk about it later in the semester. And SSL is largely a series of 4 a.m. decisions, and there have been some notable crypto attacks against it, as well as many implementation attacks against it as well. So SSL effectively provides one-way authentication for most of the time. For instance, if you're dealing with a website, you want to make sure you're dealing with the right website, especially if you're doing any form of banking or shopping, etc. And when you send your credit card information to perform any purchase, you want to make sure that whatever you're purchasing isn't altered, there's some integrity there, and your financial details are also confidential, not shared or exposed in any fashion. And on the other end, from a protocol standpoint, there does not need to be mutual authentication. Authentication can be handled at a higher level, effectively layer 7. And that's basically the domain, the business logic of any application. But SSL can be seen as existing at layer 5 if you subscribe to the OSI model. So this is the TCP/IP model, however, and the socket layer sits, or also known as sometimes the session layer, sits between the transport layer and the application layer. And SSL is essentially, is essentially you make a random request and then the recipient, say Bob, replies with his own random request and providing his certificate. The certificate provides his public key and it also provides a signature that's signed by a trusted third party that both Alice and Bob should know, so that Alice can verify that this is indeed the certificate and has a signature that I can go verify with the trusted third party's public key. And then Alice replies with her encrypted response to Bob's random request, encrypted with her own key, and Bob responds accordingly. And a common man-in-the-middle attack would be not common, but a very academic man-in-the-middle attack would be for Trudy. If Trudy can intercept all of the traffic and control the entire traffic flow between Alice and Bob to intercept the second request and substitute Trudy's certificate instead of Alice's, and hopefully the rest of the transaction would be Alice then sends a reply using Trudy's details and encryption and her key, and so on and so on. However, this is going to be easily defeated if Alice makes any attempt to verify the certificate sent in message 2. However, as was recently discovered, there was a CVE, a 0-day that came out just last week in Apple iOS operating systems and all implementations using a vulnerable, all versions using a vulnerable libsecurity SSL library. And specifically, SSL keyexchange.c did not check the validity of the signatures in the TLS server key exchange and SSL, and that allowed for any man in the middle to spoof an SSL server and intercept all traffic and intercept and decrypt all traffic going between two parties. Another vulnerability in the implementation of SSL was an antivirus application that did not check if the server's host name matched the domain name provided in the subject's certificate, which allowed basically malicious users to submit whatever certificate they wanted for any domain, and it would just accept it as long as it's a valid certificate. So this allowed hackers to basically attack the antivirus software whenever it's doing updates and other stuff as well. Another CVE related to SSL and TLS was a very serious vulnerability from 2012 in the apt-get update toolchain for Ubuntu that allowed basically attackers to install arbitrary packages, arbitrary repository keys via man-in-the-middle attack in a vulnerability in the apt-add repository tool that did not properly check the keys imported from a key server to see if they are valid at all. So it just took all of the keys provided to it in a key server response and accepted them as is. So a key server response can be completely spoofed to facilitate a man-in-the-middle attack and allow an attacker to install whatever packages he or she wanted on the victim, and that would usually install them also at root, which is pretty serious. So another protocol that failed to implement TLS properly was Google's Speedy, SPDY protocol in versions 3 and earlier. It would not encrypt or protect HTTP headers, and this, as well as other data that was sensitive, and it effectively enabled what is now known as the crime attack against SSL and TLS, and we're going to cover that in a little later lecture. And we didn't cover SSL very well in depth at all. I'm saving that for a later lecture because we have a lot to cover in this one. So we're going to revisit IPsec because it does something very similar at a lower level, and I sped through it last time. And we've covered these slides, how there's internet key exchange and encapsulating security payload. And the two different phases, well, the two different parts of IPsec, two different phases of Internet Key Exchange, and then there's two different modes of IPsec. Yes, this is all very confusing. I don't expect you to memorize it all, so just bear with me. So IPsec's transport mode is designed for host-to-host communication. It is much more efficient than the other mode, and the IP header is left untouched. It's there in plain text, and a second header for the encapsulating security payload is put in there, and the data is then appropriately encapsulated, or rather protected. In IPsec tunnel mode, it's designed to provide firewall-to-firewall communication for facilitating encrypted tunnel, much like VPN. And the original IP packet is encapsulated in IPsec, and it's going to be in plain text. And once IPsec tunnel mode has been established, there's going to be a new IP header, the encapsulated security protocol header and authentication header, and then the IP header and the data headers are going to be encrypted in this tunnel and will not be viewable by an outside attacker. So all hosts communicating over IPsec tunnel mode masquerade as the IP address for their given firewall and communicate to the host behind the destination network firewall, effectively providing a virtual tunnel between the two networks. So this masquerading prevents an attacker from knowing which hosts are talking between the two networks, and thus provides a great level of confidentiality between two networks, just at the network level, which is useful. However, tunnel mode is not very efficient, according to most, and transport mode is a little more efficient, and that's all we need to know about IPsec. It's not widely adopted as a standard protocol, I should say. So we're going to breeze through wireless discovery tools. I'm not really going to cover wireless hacking. It's too trivial. You could pick up a tutorial for any of these tools and probably do it in about 10 minutes against a web network. So Kismet is perhaps one of the most mature tool sets that can do 802.11, layer 2 wireless sniffing, detecting, and I guess hacking. It requires that a wireless card has raw monitoring mode, and that may be limited by the hardware and or drivers for the hardware. So there are various different plugins to the Kismet platform that allow sniffing other media and other protocols, and these are all community written. Aircrack and the Aircrack NG suite is useful for attacking WEP and WPA encrypted wireless networks, and can recover keys given enough packets have been captured for both. It's pretty straightforward. You're not required to know this stuff. ASLeap is another one. Wireshark is not just for wireless network hacking. We're actually going to have at the start of the next lecture, a video on using Wireshark to do forensics on botnet traffic, and I'm going to go through PCAPs for common crime kits and botnets such as CryptoLocker, perhaps Zeus, and so we can explore how we can investigate malicious traffic, identify it, and perhaps respond to it, if not provide forensics analysis about it. So Wireshark is perhaps the best open source network packet analyzer. You should never run it as root. Always follow that warning. if you're going to use it for any form of intrusion detection or incident response, you should be using TCP dump, piping it to a file, and using Wireshark and non-root mode to open it up if you need a GUI to view all the stuff going on in it. So it can do all these things on the slides: troubleshoot network problems, examine security problems. Say if you have a device you suspect it has a rootkit on it, you cannot use any of the diagnostics provided by the device from ring 0 to 3, if not below 0, all the way if it's a IPMI rootkit to -3. Anything that device may tell you could be a lie. However, if it's part of a botnet or communicating back to a network, it can't lie about what it sends over the network. So if you plug it up to a network tap and you capture all the packets and then open them up perhaps with Wireshark, you can examine security problems. From a developing stance, you can debug protocol implementation problems, and from an educational stance, you can use it to learn a great deal about network protocols in general. So there are some sample PCAPs at this URL. However, more interestingly for us, these two URLs provide PCAPs for general network security, and the last one provides very interesting PCAPs for botnets and malware. And you can see exactly what the malware is doing when it dials back to its host and then establishes the rest of, well, its automated intentions. So TCP flow is another useful tool, very similar to Wireshark. However, it's more concerned with taking an entire flow, whether it's a whole TCP session or whole UDP session, scraping out the payload and reconstituting it into what is entirely sent from each application down to the lower networking layers, such as layer 4, layer 3, etc. So TCP flow will allow you to scrape out like entire PDFs from a PCAP and entire images and spreadsheets and whatever is sent just over TCP will allow you to reconstitute those files in easy to read format. So discovering hosts on a network is important for determining whether or not there are unauthorized users on your network, as well as detecting targets on a network. So a host may be on a network and may be, say, asleep or may be very active. Perhaps it's an infected system and it's after midnight and no one's at work and it's sending out a ton of traffic. Perhaps it's exfiltrating secrets while no one's at work, hoping that under the cover of night it can get away with it, or at least go unnoticed. So there are various ways to determine the liveness of a system. If you have network monitoring capabilities at a firewall, that's very easy to see in many graphical formats provided by a very, very wide variety of network flow monitoring tools, usually just called net flow monitoring. But if you need to discover hosts, there's ICMP, and ping is an obvious choice. However, ping is commonly seen as a security threat, and many networks have some form of blocking policy on ICMP protocols. There's also nping and a tool called Superscan, which is more Windows, I believe. Never used it though. So there are a number of ICMP message types. Here are a few of them, and they can be used for discovering a host on the network, whether it's up or perhaps if the destination is reachable, and thus is implied that destination or host is down. There's also nmap and nping, and nmap is an old tool that's commonly seen as a Swiss Army knife, but it is slow nowadays compared to advancements. And you can scan for those well-used ports under 1024 to see if it's running any common services, and that might be a quick way of determining how lively a system is, whether or not it's up or not as well. However, this is not very scalable for a large network, its approach at least. It does a lot of blocking to prevent saturating the network so it doesn't DOS a given bottleneck with its scanning traffic. And nping can be used to discover hosts via TCP UDP, and it effectively queries several common ports such as port 80, port 443, and replies back the results of such queries, and it's pretty quick. There are other ways to do host discovery, especially if you're on the outside and the DNS server is misconfigured. You might be able to do a full zone transfer to an imposter DNS server that you set up, and this will allow you to map the entire internal network. I don't really want to go into more of the details on this for various reasons. So past detecting whether or not hosts are up and mapping a network, there is port scanning, which, as I've already said, and techniques related to it that allow you to determine what each host is running. And so basic connections over TCP or UDP to a target system lets you determine what hosts are up, running, listening, and will reply to basic requests. So there are various different scanning types. Full TCP connection will do a SYN and whole standard connection and then tear it down normally with a fin. Certain scans will just do SYN, not worry about the handshake, just look for the reply back. Similarly, sending perhaps a fin request and seeing if there's any error messages saying, hey, this is a packet out of the normal state machine, this is an error, et cetera, et cetera. So Nmap has a lot of different flags, more than most people understand, and can do a lot of different things. However, it can be quite cumbersome and is also very inefficient. And I opt for ZMap, which came out August last year, after this original class in spring 2013. And ZMap is just downright awesome. It can do, I believe, everything Nmap can do, or at least facilitate and equivalent Nmap functionality much, much quicker. ZMap can, with a single PC and a decent internet connection, scan the entire IPv4 address space in under 45 minutes. And I provided links to it here. Here's a basic table from the slides for ZMap's original presentation. It can scan 98.7% of the internet in, I believe this was an hour and 9 seconds, hour, 9 minutes, 35 seconds. Whereas for Nmap, it took 62 days and could only get 81. Oh no. For single, I forget. But it's much, much quicker. And this is compared against Nmap's configuration of Insane, which is the most aggressive, I believe. However, I don't use Nmap that much. So being able to map out the entire internet lets you see a lot of problems and a lot of vulnerabilities that perhaps most system administrators wish most other users or wish weren't publicly known. And so this slide is taken from the ZMap guys. I believe it's worth talking about the ethics of doing active scanning. It's impossible to request permissions to, when you're trying to survey everything on the internet, to request permissions from everyone on the internet. That's just totally impossible. At the web level, for the World Wide Web, most search engines and web crawlers do some form of basic permission request to see, hey, do I have permission to just look for all possible things on your web server? And the file that is first requested that provides these permissions or specifies what the owners of that web server allow people to do, although there's no enforcement of what is allowed and not allowed, is something called robots.txt or .robots file, and that specifies that, hey, you can visit these files on my web server. So since there's nothing like that at the network layer, there's no way to know whether or not administrators want you or don't want you scanning their network. So some administrators may react hostily, and in their presentation they discussed that I believe when they scanned the entire internet, they received hostile responses via email from, I think, 15 system administrators, and they were outright attacked by 2 networks with denial of service traffic, which was very interesting. So what ZMAP does in order to reduce the impact that its scanning does is distribute the load of its scan randomly so that it's not iterating across the network from address 0 to address 1 to 2 to 3 to 4 to et cetera, in an incremental way, such that it would be very bursty to receive such traffic. Instead, it aware levels it to randomly order the host that's scanning, so your network won't be scanned all at once. It'll be scanned over the 45 minutes it takes to scan the entire internet, which will go completely unnoticed to most system administrators. So it also makes an effort to honor, if there's some way to handle it, the request to not scan my network if it's provided. I believe there's a configuration file that's, I think, like a blacklist file that ZMAP loads, and you can specify subnets to avoid. But there's also other tools, SuperScan. I've never used this, but it's nice and has a GUI. So past detecting what services might be on a network, you might want to determine the operating system that provides it, as well as perhaps the implementation of the TCP/IP stack for that operating system. And differences arise because humans interpret specifications differently, and vendors will interpret the RFC differently for TCP because it's a little complex. And so the nuances in how things are implemented differently allow you to fingerprint these things. So this can also be used to, if you can detect exactly what version something is, you can provide all the known vulnerabilities for that version. And this can be integrated to provide basically a vulnerability scanner. And tools like Nessus will provide that at a network layer. However, Nessus has gone from free to now you have to pay for it. So very basic fingerprinting is if a protocol is verbose, it may provide a lot of information from its very first reply. And if it does, you can do what's called banner grabbing. You simply just netcat or connect to the service, and it will tell you all these things. For instance, web servers usually reply with what version of HTTP they are, a HTTP response, the current date, what server it's running, perhaps what operating system it's running, et cetera, et cetera, et cetera. And this tells an attacker a great deal. For instance, if this particular version of Apache had a 0 day that allowed me just to send it a couple packets and I own it, well, the attacker is not far away from compromising your system just with this information you've given. There's also another protocol that I believe has largely died out, but is unfortunately very common in critical infrastructure. It's called SNMP. I like to call it security is not my problem, SNMP. It stands for Simple Network Management Protocol. It will tell you almost everything about a host, and was designed for managing networks and make it very, very simple. However, it's extremely insecure, and usually protected by weak passwords, and it only allows um, uh, passwords under a certain length. And once you can compromise the password, I don't believe there's any brute force penalty. You can just sit there and crack away at it, or break the weak crypto that's used to communicate it, or encrypt the session. There are tools such as SNMP util and SNMP walk that allow you to enumerate all hosts on a network, their operating systems, their applications, all the users for each operating system and each host, and perhaps their password hashes as well if SNMP is set up to be so friendly, which is just beyond ridiculous. So if you've amassed all of this data, it can be a lot to keep track of. There are tools to basically fill the data into a database. Metasploit has, I believe, SNMP modules and Nmat modules that just plug the results into a database, which is very easy for generating a report and managing the data. So we've covered these layers so far, and we're going to go back into exploitation and explore networking shellcode, and specifically port binding shellcode. We're going to explore how to, instead of, before I get ahead of myself, we're going to explore how to exploit a system and get it to pop up a service that we can connect to, a new service on perhaps a new port. So, in the textbook, the CD provided to it has a application, tinyweb.c, that has a very, very simple buffer overflow vulnerability in the receive function that receives data to the service and stores it in destination buffer, and it's very easy to buffer overflow it. And we're going to look at it with these slides that Professor Lewis put together that have it opened up with GDB, and discuss how to write shellcode for it and how to write shellcode that will pop a shell that we can connect to. Because if you just tell it to pop a shell, it's going to spawn it on that server locally, and there's going to be no one accessing it. It's going to be useless, and our exploit techniques so far have only been for local privilege escalation. So what we need to do is run the service and attach GDB, the debugger, to it. -Q, I believe, tells it to use symbols. -PID tells it to attach to this process. So what is done, we run TinyWeb, we get the process ID, which is 13019, and we specify to attach GDB to this process and to use the symbols provided in this binary. We haven't talked a lot about symbols. Symbols are things in source code that make it readable for humans. For instance, when you're using a variable int x equals 5, when it gets compiled, the variable name doesn't get translated into the binary. So you lose that symbol, you lose that information. Similarly, for a function, say int foo, and the arguments for it are int a and int b, the arguments are going to be accessed relative to the stack pointer, and you're not going to see variable names for them. So those symbols are lost. The symbols for almost all variables are lost. However, the function name foo, usually by default that symbol is preserved, and you'll see a call foo or a call printf or a call exit or call socket or call connect in the disassembly, and that information is facilitated by symbols that are provided in the binary by the compiler. So we're telling GDB to load the symbols that are provided by a.out, which is, since we've just called GCC and not told it what to specify the output as, it's going to use this default a.out. So this is going to let us view the basic functions um, that are preserved in the binary. So what we need to do is set a breakpoint at, for the source code, handle connection. If you have the source code up, it's at line 62 in tinyweb.c. You can pause the video now to load up the VM and look at the source. It's really concise. Essentially what's going on is there's a 500 character buffer called request, and it's vulnerable to a buffer overflow that allows you to write up towards ESP, obviously towards higher memory. Um, overwrite the return address. So what we are doing is we are going to have to find where this buffer occurs on the stack, and if we have GCC specified to provide all the symbols it can, however, it will provide the symbol names for the variables. So we're able to just tell GDB to tell me what is that request. And so request will be at this memory location, and it will be all zeros because it's zeroed out. And so tell me what is that request plus 500 will specify that at this location this memory address is. This was all facilitated by telling GCC to compile with the -G flag, which tells it to be as verbose as it can when preserving symbols and provide as much preserved symbols as possible. So that's useful for facilitating exploit development on a open source project. However, many many applications and products out there are compiled with symbols completely stripped out and some mild form of obfuscation going on, as well as perhaps just a CD key involved, and the logic to check it may be spliced throughout the application code. But I digress. So we've loaded up GDB, attached it to the process. We set a breakpoint on handle connection, and we know to use that breakpoint just because of the source code provided to us, and I've skipped that part. I encourage you to go look at it if you haven't already. Then we look at basically request, and this is the destination buffer for the vulnerable function that vulnerable line of code that calls the vulnerable function right after handle connection. Handle connection basically is the function that has this code. And so receive line, when we call it, is going to put all the data that it reads up to a null terminating character or a terminating end of file character into request without caring what the size of request is. So the following GDB commands allow you to view what is that request plus 500, and then using the address here plus 4, 8, 12, and then 16 would be down to the next line. So this is why this is plus 8. It allows you to see what this is if you couldn't see it just with here, but the slides are illustrating that you should look here because this is going to be where the return address is. And if you've worked with a debugger long enough without ASLR on, it's pretty easy to recognize where a pointer to the .text segment is, because it usually starts with 080 something. And so by viewing the memory just after requests end, which is 500 characters at the beginning of a request, you can incrementally try each one to see if it is indeed a pointer back to the text segment which would thus be on the stack, the return address that's been saved. So after determining where the return address is, effectively, what you want to determine is how long of a buffer do I need to fill up in order to start overriding the return address. And so the math here is that it's instructing GDB to print the difference between the start of the request buffer to the provided here we go, provided return address, which is the BFFFF7D4 plus 8, which is BFFFF7DC. And so the difference there is 540 bytes. So the general technique is that what are here in the slides is not the only way to do this. I'm going to say one way, and then I'm going to address what's on the slides. With the 540 characters that you have up to the point where you're targeting the return address, you can put in shellcode, and you can tell the return address to point directly to that shellcode, and you can make the targeting easy by appending NOPs or NOP sled to the front of it. We've covered this already. Or you could fill it up with garbage, or a combination of a NOP sled, then your shellcode, then garbage, and then overwriting the return address. That's a very, very common technique. And the garbage may be NOPs behind it as well. Or what you can do is fill up all 540 characters with garbage, overwrite the return address, and then after that have a NOP sled, have your shellcode, and then your null terminator. Obviously, it takes up much more space than the 540 characters plus a pointer. You may not have that much space in the destination buffer, which is something to keep in mind. So, in all cases, you're going to have the return address being overwritten to point to your NOP sled or the beginning of your shellcode. And it's important to note that in network programming, the null byte is not always the terminator or end of file or null terminating character. Often network applications instead use the line feed new line characters. These are two characters to terminate user input or terminate a string. Usually the reason is that applications in each packet, you're not just going to want to send, if you're sending, say, your first name and your last name, a packet just containing your first name, and then a packet just containing your last name. You may have multiple strings in a packet, so they may have, they're obviously going to be null terminated. So you can't terminate your whole packet with null terminator. You have to use a new character combination or a new terminator. So the decision very early on in networking design, operating system design, was to opt for the line feed new line character combination to specify that this is the end of the application data in this packet. So we're going to have that as the last character on our shellcode. So in order to have a useful exploit, as I said, if we spawn, just tell it to spawn a shell with the shellcode we've written so far and tried to do so far, it's going to be pointless. It's just going to spawn a shell, a local shell on that remote server, and we're going to have no way to control it or influence it. And I don't believe any user on that server will have a similar opportunity. So one of the most simple approaches is to exploit the service and fork and listen to any connections on a new port that we've opened up, and we'll provide connections to that port a shell or shell access. So The following shellcode, you can find the source for it in TinyWeb exploit2.c on the book's source code. And we're going to dive into how to write such shellcode. There's effectively 4 main functions we have to call in our shellcode in order to handle accepting connections to a specific port. So the functions are highlighted in orange. There's the socket call, the bind call, the listen call, and the accept call, and all the code in between is simply setting up the data structures that are needed to facilitate these calls. So socket is going to establish the socket. It's going to return a file descriptor, which is going to be an integer. So sockfd is going to be an integer. And for the socket, there are various options that are specified, usually in a socket library .h, I forget, somewhere for the version of C, and they specify AF internet or PF internet, whether it's TCP stream, sock stream, or UDP, and I forget what 0 here is, or I believe that's the IP address, and so 0 specifies any. So what's happening here is that host adder, this is a struct of sock adder in type, and host adder is being set up to have the host byte order setting specified, which is AF inet, the port to be used, and that's translated to the appropriate byte ordering for the given network. You'll cover this in networking classes. Not necessary to know this at the moment, and I don't believe our exercises or tests will worry about network ordering. Everything will be the same endianness, and that's what byte ordering means: little endian or big endian. And x86 is all little endian. So by specifying in the last option for the sock adder that the adder should be in adder any, this flag specifies for bind or whatever is using this to automatically fill with this current machine's IP address. The code after this, memset, zeroes out the rest of the struct so it can be safely used. And this is all legitimate code that we're trying to understand so we could write our own shellcode to mimic it. Then the bind call passes in the file descriptor, which is, as I said, an integer provided by socket as the first parameter, and then the host address structure. Effectively, is tying this file descriptor to an address, an IP address and a port, as well as a family specifier, so they can communicate properly all the transmitted and received data and any errors, and transmitting it to the appropriate file descriptor. Then finally, once the socket is binded, it can begin listening on the socket, and accept is a blocking call that waits for any connections coming in over the socket and will handle them by returning a new file descriptor that allows communicating with that new connection. So we're going to have to understand socket call. It's specified in user include whatever your architecture is. In this case, for the book, it's i386, and UNI-std.h is the given library or header file that specifies the socket call table. So we covered the system call table and how one is exit, and there's other things, and you put them into EAX to specify what system call you are making. And so socket call is the system call 102. So you put that in EAX. However, socket call has its own library of different functions. And so to specify what type of socket call you are making, you put the appropriate function call number in EBX. So EAX stores the system call, EBX stores the socket call, and then ECX is where the arguments start. So ECX, EDX, etc., etc. Obviously, whatever calling convention is being used, whether it's CDECL or fast call, will obviously influence how this should be done. And we're going to cover fast call later in the semester in the return-oriented programming lectures. So we have this table of socket call functions. There's just socket, there's bind, there's connect, there's listen, there's accept. We've already looked at socket, bind, listen, accept, and we need to write shellcode that calls them the same way the previous sample code did, so we can tie that together with an exploit and provide a remote shell. So in order to pull off passing a structure, which is what bind has to deal with, we have to point an address to a structure, but that structure we need to construct. So we need to know how it looks like in memory. So is it going to have like each field in the struct be padded? Maybe there's some cookie, maybe there's zeros, maybe there's no padding. Well, for GCC compiler and most compilers that I know, structs are just arranged flatly in memory. Obviously, there's basic memory alignment that has to be complied with, and effectively for the the host adder struct, there are 4 parameters that we have to fill out. And there's the short, which is there's the SYN family, which is a short. There's the SYN port, which is also a short. There's the SYN adder, which is 32 bytes for IPv4. 32 bits, I'm sorry. And then the rest of it is going to be zeroed out for bind to set. So if we look at it in GDB with all the symbols compiled, which is obviously not default, we can do things like just print host adder, and it's going to tell us for this line of code when we break on it that it's going to be a struct with the SYN family set to 2, the SYN port set to this, the SYN adder set to adder any, which is going to be set to whatever this host IP address is, and so on and so on. You can see that if we're going to have to set this up, there's going to be a lot of null bytes in here, and we're going to have to figure out how to work with that. So if we print what the hex is for 27002, which is going to be the port that we're going to open up, that we're going to connect back to. The attacker is going to connect back to the victim once we've exploited it. It's going to translate to 697A. And if we look at the memory here in the stack, it's going to be 697A. And obviously it's little endian ordering. And so for just 2 bytes, this is actually a short. So that's how we determine that this is a short if you can't read that from the source code for the socket family calls. And so similarly, this is also short, and say the 4 bytes here, 32 bits here are for the IP address or the socket address, and then the rest is all zeroed out. And if you do size of struct sock adder, it's going to return 16 bytes, and so that's why 16 is used here in this instruction. to print out 16 bytes, starting at the address pointed to by host adder. And so, given that we had to call, going back, host to network short, this establishes this encodes whatever short is given to it to the network byte ordering. So 31337 is going to get reordered to it's going to be represented in hex, and it's going to be reordered in little endian. So that's why 697A is actually 27002, and if you undo the reordering, it's going to be 7A69, which is 31337, which is why, if you're trying to understand why this port is specified does not match the one that was immediately recognized, that would be why. So now that we understand that structs are just flat is just a flat arrangement of data in memory that just has to comply with the alignment restrictions that all processors have to comply with that we've already talked about earlier in this semester, we can go about putting together some very basic shellcode that can XOR out what we need to and push the values that we need to accordingly. So in order to call socket, we're going to pass it 3 integers, and the first one is going to be, going back, PFINet, sock stream, and then 0. And what we've done in the slides is just translate whatever these flags to the integers that they map to. Most flags in networking map to just an integer or a short. So the equivalent of that call is just calling socket, providing it 2, providing it 1, providing it 0. That's PFINet, and that's TCP. And then this is, I believe, to tell it to use, I forget. But anyways, so we have to first push into EAX the system call number for socket call, and then into EBX we have to make the similar setup for whatever function in socket call we're calling. So that's going to be the socket call. So what we do here is push byte hex 66, which translates to 102 in decimal, and we pop it, which is effectively just a concise way of setting EAX to byte 66 without any null bytes in it. CDQ is a silly and over-engineered instruction in x86 that you're not going to have to know about for this class, but if EAX is even, calling CDQ will XOR out EDX. That's one of its main purposes in exploit code. Then we have EAX set up, we have EDX set up, and we're going to use EDX later. Now we set up EBX, so we XOR it out, and we're going to have to set it to 1. And then we begin the arguments for the socket call, so 2 and 1.0. And so we have 0 in EDX, and we push the arguments from right to left on the stack. So we push 0, then we push 1, then we push 2, and then in ECX goes a pointer to the arguments for the given socket call function. So we move the stack pointer to ECX, and the stack pointer, since we just pushed our values onto the stack, will point at AFINet equals 2. We'll push byte 2 will point right there, and then we call the system call, and that will call socket. And so sockets system call will store the result in EAX, so we need to move that to ESI or some register for being used later. We're gonna have to keep track of it. Then what we want to call is we want to bind the socket provided by this function to the following struct that is going to be a sock adder struct, and we're going to have to set the first argument to 2. We're going to have to set the port to the host ordering, host and network short ordering, so it's reverse ordering for whatever value we specify. So we translate the hex and then we do little endian reverse ordering on it. So 7A69 is at the end of the day going to be on the wire 697A, and then and then the last value, if you specify any integer other than 0, it's going to use that as IP address. But if you specify 0, it's going to tell bind to use my IP address. And then lastly, the size of this struct, and that's going to be in bytes. So the first thing we do is, since EAX has been trampled over by the socket call, we're going to have to restore that, and that's why we saved the return value that was put in EAX into a different register so we can keep track of it. So we're setting EAX to the socket call family again, and then EBX, we know from just actually experience that it's not going to be trampled by the system call, and EBX will still be 1, and so we increment it again to get 2, and so that's specifying what socket call function we are going to use, and that happens to be bind. That's where the 2 is. And so EDX is going to be 0 still, and then we're going to push again from right to left 0, the reverse ordering for the port, and then BX, which is the lower half of EBX, so that's going to be just 2 bytes, which is going to be a short, and the rest of the code is that we're going to have to move again after we've pushed all this stuff to ESP, so we're providing a pointer as the argument here in ECX. This is how this is all handled by socket call. So after that, we push 16. That's the size of the socket struct, the sock adder struct. Then we push ECX, which is going to be a pointer to ESP at this point, and we're going to push ESI, which is finally the descriptor provided for the socket. And then we call the interrupt to do the system call, and it's going to bind the socket to this IP and port address. Then you can begin listening to it. So this following shellcode moves again, since EAX is trampled. We're not going to check the return for bind. It returns 0 on success, and our shellcode is not going to be complicated enough to do any form of error handling. So if for some reason it was not able to bind to the address, for instance, if that address is already in use, this is all just going to fall apart. But moving on, listen is going to I forgot to explain that we're moving the stack pointer at this point into ECX, so we can point to all the arguments so far, and that's needed for the socket call. So in order to do listen, we again set up EAX to have the system call number 102 to access the socket call API. We're calling the listen function, so EBX is still 2, and going back to the table, we're going to need to make it 4, so we increment EBX twice to make it 4, which is sys listen. This should be tabbed over, ignore listen parentheses, that's not a valid assembly. Then we push EBX, which is going to be 0, or rather it's going to be 4, sorry. And then we push ESI, which is still going to be the socket file descriptor. So we're pushing from right to left, 0 or 4. I don't think it matters. And then we push the file descriptor. Then we save the pointer to this struct into ECX, and then we call the system call. We don't care about the return address for listen. I mean the return value in EAX for listen. And we continue. We know EAX is trampled, so we set it up again. Then we set EBX to what sys accept is, so we can make the accept socket call.
Hi, this is Taylor Johnson.
And I'm sorry. So we set up the socket call, and then we set up EBX to point to the appropriate sys call. Then we, in EDX, we have 0 still. So we push it twice to push 2 zeros onto the stack. And then lastly, for accept, you specify what socket you're accepting on, and it's going to return a new socket file descriptor. So we tell it we're accepting on the socket file descriptor that we've been keeping track of in ESI, and then we save the stack, the pointer to the struct into ECX, and we make the socket call again, and that is how it's all done. However, you need to now tie it to spawning a shell. So sockets are just file descriptors that can be read from and written to, and by swapping the standard input, output, and standard error file descriptors for a process with a socket via the dupe2 system call, you can tie everything going in and out over a socket to the standard in and out and standard error of the process. So if we have a process that we spawn as the shell and tie all of the standard in, standard out, and standard error to the socket that we've told it to bind a listening port to, we can allow for an attacker to connect. We can allow for our attack to connect back to the service that we've exploited and popped a new service to spawn a shell on over this new port 31337. So dupe2 is very simple. It takes 2 integers. The first one is for our purposes, going to be the socket that we're setting up, and then we're going to pass it standard in, standard out, and standard error. So standard in is going to be 0, standard out is going to be 1, standard error is going to be 2. So by by continuing the shellcode, by moving the socket file descriptor that we had in as returning from accept, because accept returns a socket descriptor, it's going to return it to EAX. We're not using what we stored in ESI, we're using what's returned by accept. By using what's in accept, we put it into EBX. Now remember, we're not going through socket call at this point. Dupe2 is a standard system call. So the first argument is going to be an EPX. The second argument is going to be an ECX. So by XORing ECX with itself, we're setting it to 0, and then we call it, and this is effectively calling dupe our new connection 0, and then we increment ECX by 1 and keep doing it, and then increment it again and do it again. And what is resulting is that it set up the file descriptor so that the standard in, standard out, and standard error for this process now all is tied to the socket that we have accepted a new connection on. At this point, if we spawn bin.sh, this is all very familiar shellcode, it should be, it will spawn a new process that connects, that provides all its communication over the socket, providing a remote shell. So we're going to explore later how to minimize some of this very verbose shellcode. It does a lot of simple things in covering branching control structures and actually having shellcode that performs loops, but we'll do that later. So the reason this is all relevant is boring old buffer overflow, I know. However, such a boring old buffer overflow is found in Python's default networking libraries, specifically the function receive from into remote shellcode. Receive from into remote buffer overflow vulnerability, and the code to exploit it all is very, very simple. And academic code like a vulnerable receive from function actually does exist out there in the wild, and this is proof that these boring old examples actually can manifest as real vulnerabilities.